Hey guys, welcome back. Today we're going to be talking about soils. Are one of those really cool topics in geology that unfortunately we don't spend enough time on, if you ask me. There's a whole science behind soil formation, and it's basically an offshoot of erosion and diagenesis, things that we're going to be talking about from the past lecture, this one, and into the next one when we get into full-on sedimentary rocks. So with that said, let's go ahead and actually describe what soils are, get through the science a little bit, and find out why they are in fact so cool. Okay? Well, soil is a combination of mineral and organic matter, water, and air. If you remember from one of the earlier lectures, we talked about how was the hydrosphere, the geosphere, the atmosphere, and the hydrosphere all coming together. And interacting. And the place where they do the best interacting and create kind of the optimal conditions is actually right in soils. Okay? So here we see a typical cutout of subsoils, and we'll notice that it almost looks like it has these layers in here. And we'll actually describe what these layers are. They're very, very neat, and it actually turns out that the science behind them is pretty straightforward. You'll be able to understand it by the end of this class. You'll look at this and be able to recognize instantly what is happening here in this picture. As a matter of fact, we might actually come back to this picture at some point because it's just such a good one. So anyways, that portion of the regolith, here's a nice little vocabulary word that I want to make sure that you know. Regolith, which is rock and mineral fragments produced by weathering. Okay, so it's busted up rock from weathering that supports the growth of plants. Okay. Remember, I was talking about those four spheres. Here we see them again. So this is typical components of soil that yield good plant growth. This is what you want. It turns out that soil is about 45% minerals. So less than half of it is actually mineral matter. About 5% is organic matter, bacteria, decaying roots, maybe some moss, things like this. And of course, there's water. Believe it or not, there's actually water in the soil at all times. Good soil is going to have about 25% water in there. And then the rest of it's going to be open air space. There's going to be some good air transfer that's going to be moving between the roots and the surface of the air. So basically, the soil will be, in a sense, kind of breathing, if you will. 25% air volume. Okay, it's kind of hard to believe that there's that much air in soil, but there in fact is. All right, so there's several factors that you need to be aware of when we're going forward. So, like I said, the science of soils is very complicated. We could spend an entire lecture just dealing with parent material, another one on time, another one on climate, another one on plants and animals, another one on slope. But we're just going to go ahead and just buzz through it here in this lecture, and unfortunately, that's the amount of time that we're going to have in the class on it. So there's lots of books, by the way, you can read up on this. But anyways, parent materials. This could be residual soil. This is the old stuff that was there before. Parent material is the underlying bedrock. So right there, maybe the soil is forming from the rock that it's actually sitting on top of. Another way is transported soil, right? Sometimes soil comes in from somewhere else. This forms in place on parent material that has been carried from elsewhere and deposited. All right, time, of course, is important in all geologic processes, and the amount of time for soil formation varies for different soils depending on geologic and climatic conditions. So geologic, remember, certain minerals tend to break down very easily, such as your calcium plagioclase, but things like quartz do not. And then, of course, climatic conditions are also going to be very big. Climate, which is probably the most influential control on soil formation. Many key factors are temperature and precipitation. As a matter of fact, these are probably the two most important factors for determining what kind of soils are going to form. Okay, plants and animals have a huge role to play. Of course, the organisms influence the soil's physical and chemical properties, and they also furnish organic material to the soil. And then, of course, steep slopes have poorly developed soils, right? Because whenever the water comes, it washes it right off. And the optimal terrain is a flat to undulating upland surface. You can kind of think of the Great Plains of the United States, of North America that way. There's also areas in Central Asia that are also quite good in this matter. So here we can kind of see the three general areas where we can see where soil will tend to develop, but sometimes it will last and sometimes it won't. So here we see soil is going to form. Here's a cross section here in the river valley and these cliffs, and this is an image of some cliffs here. You're not going to get a whole lot of soil development because of the steep slope, right? There's nothing much is actually going to form here. You get some, but not much. Okay. And the reason why is every time it rains, it just washes it right down into the valley. All right, so this all gets transported down into the valley where the river is. And that's going to put us onto a transported soil. Remember, this is transported, which is material that was brought in from somewhere else. And here we can see these unconsolidated deposits down here at the bottom of the river. The river is kind of working its way through here. And this, it turns out, is actually a really great place to grow a lot of aquatic, things that require a lot of water, I should say. The problem, of course, of growing crops in here is that tends to flood and wipe out your crops from time to time. Okay, and then of course, probably the best place are the residual soils that is developed right on the bedrock. So over here we see thick soil that will tend to form right on the bedrock. Here we're getting a little thinner soil because it's going to be on a slight slope. Here there's none, and here's quite thick horizons of soil, and of course we get horizons of soil in here as well. Okay, so the way that this comes about, it turns out that there's a process behind it. Now, it becomes actually pretty obvious that there's a process when you look at the very first picture. This did not form from a magma chamber in this way. This had to have occurred over time, and in fact it did. And this is a pretty typical set of horizons that we see. First off, you got basically a topsoil and a subsoil. The topsoil gets, there's two kinds of important things that we need to keep in mind here. There's the organic matter up here at the top. In this case, it's going to be the grass and the tree. So anything that falls out of the tree, like the leaves, will become part of that organic matter. And that's what we call the O horizon, right? So these vertical differences are called horizons. The A horizon is the organic matter mixed with mineral material. And sitting above, sitting below the O and the A horizon is this E horizon, leaching by downward percolating water. So you're going to have a lot of water working its way through these plants. It's actually going to pick up a little bit of acid while it goes through these plants for some sophisticated reasons. And basically, that acid is going to strip out a lot of the nutrients and percolate things down, especially clay minerals and iron oxides and calcite, things like this. And so we would actually tend to see an area here that is lacking a lot of minerals that would be discolored, usually to a lighter color. So let's go back to that original photograph back here, and here you can see it, right? Here's that horizon over here. So here's our A horizon, here's our O horizon, this grassy material up here, okay? So that leaching area is called the E horizon. Now, sitting above the E horizon, sitting below the E horizon is the subsoil. So everything below this light-colored section is the subsoil, and this is where you get a lot of that percolation, is washing a lot of the clay minerals and iron oxides and calcite down lower. And this is basically where the rock is being broken up over time. In this case, the roots are helping break it up, but they're breaking up the unweathered parent material, or actually the rocky material. So again, let's go back to this original one. Here we can still see the rocky material still in the soil. It's still breaking it up over time. But here you can see it clearly. Here we've got an O horizon, A horizon, an E horizon, and then everything down here is going to be the B horizon. This is it's actually the zone of accumulation. So the stuff that was in here is washing down into this tanner area down here. Okay. And then, of course, the C horizon, the material right on top of the bedrock that's breaking up, and then the bedrock itself. And so this would be an example of exactly what we were describing. Here we have the O horizon up here on top, a very nice and well-developed A horizon. And sitting right below it is this patch. This is a mollisol, by the way, in coastal Oregon. Mollisol is a soil that forms in grassy areas. And so here we see an area of leaching very clearly right in here, okay? Really nice horizons in here. We're not going to get into the nuances of this, but here you can actually start kind of detecting that there is some soil material that's actually sloughed off the top here. So don't think that this is bedrock material down here. Okay, this just fell off this cliff. Here's another set of horizons. You can actually tell this one right away. This is what they call a paleosol, which means an ancient soil. It's very, very old, and this is from a trench that was dug in the United Kingdom. And here we can see again, here's the O horizon, here's the A horizon. So this is that really good zone of good productive soil right here on the top. This is where all the organic accumulation is, that nice A horizon. Notice it's not very thick here. Because right below it is the E horizon. So the E horizon here, and unfortunately we don't have a tape measure, but this is probably about 4 inches thick, sitting on with 6 inches of A horizon on top of it. So it's not a real thick horizon. And then below it, going all the way down, and unfortunately we can't actually see the C horizon, but this is all B horizon material. We can actually see some busted up material in here. So this might actually technically, we might be able to start calling a C horizon in here if we wanted. But anyway, here you can clearly see the different units of soil development occurring. All right, so it turns out there's different ways to characterize soils and describe them. Soil texture is one of the best ways to do this. So usually you could take the amount of clay and the amount of silt and the amount of sand, and you could put on a little chart. You might be, especially those of you that are only experienced in the humanities and looking at the way charts are developed there, it's pretty uncommon in the humanities to see what they call a ternary chart. In sciences, it's actually fairly common. So let's go ahead and get acclimated to how to read one of these. So in this case, we see that it's a triangle or a ternary diagram. And if we wanted to know something that was 50%, or I'm sorry, 33%, 33%, 33%. In other words, 1/3 silt, 1/3 sand, and 1/3 clay. So this would be the clay up here. This would be the sand down here, and the silt right here. That'd make it all evenly distributed, right? So we would go to some point out here, right about here, matching out over here, and that would put us right in the middle of our ternary diagram. That'd be a clay loam. So a clay loam, a loam is actually a kind of soil that has a combination of sand and silt in here. So pure silt, if it's got a little bit of sand in it, it becomes a silt loam. If it becomes 50-50, it's actually a loam. And so this is a word that is used by soil scientists all the time. If it's just mostly clay, even if it has a little bit of silt and sand, the clay actually dominates the texture. And, clay is kind of sticky. It tends to, you can ball it up and do all kinds of interesting things with clays. So anyways, here would be the clay sector, and it kind of dominates this whole apex of this ternary diagram. So anyways, if you know the amount of material you have, silt, sand, and clay, you can go ahead and describe it as one of these textures. Silty clay, sandy clay loam, or whatever. And every soil scientist in the world would be able to look at this chart and know exactly what it is that you're trying to describe. Another way that they kind of describe these things is through something called soil taxonomy. This is very similar to how they classify organisms, right? Organisms are, they have a kingdom, phylum, and all the way down to species. Soils kind of do the same thing. And they all start with kind of 12 major orders way up at the top. And this is an image taken from the the Natural Resource Conservation Service of the USDA. You can actually get this, I believe, for free from almost any USDA office. And anyways, it's a picture of the 12 major orders of soil. So, here's your andesols and iridosols and entosols, and we'll describe what all these things mean. But anyways, these are nice images of what they are. And if you get one of these charts, which you should be able to get online, if you choose to get one, it will describe what these soils actually mean. But we're going to give kind of a brief introduction to at least a couple of them right now. So soil taxonomy is really the way that soils develop, right? So here we actually see the different kinds of soils, entosols, and over on the other side are oxasols, another group called the mollisols, which we described earlier, and iridosols.